Okay, I think maybe it's going. Okay, 05, adding probabilities. So this was the left-hand side of the sheet that we filled out yesterday. The back side here, 06, is the right-hand side, okay? So adding probabilities, let's go ahead and fill these in. All outcomes are equally likely in a simple probability model. D. All outcomes are equally likely. Like rolling a dice, as long as it's not a rigged dice. You have a 1 in 6 chance of getting any number on a dice in a simple probability model. The outcome that actually occurs.
A.
E. E is experimental probability. Let's just skip down to the fourth one. The outcome you expect to occur. B, theoretical probability. So in theory, when I flip a coin, if I flip a coin 10 times, I should end up with 5 heads and 5 tails, right? Because 50% of the time it's heads, 50% of the time it's tails. Does that mean that if I flip a coin right now 10 times, it's going to come with 5 heads and 5 tails exactly? No. So that's the experimental probability versus theory. It should be 5 and 5. Okay? A model used to represent an outcome of an experiment. A, probability model. Okay? And the last one, a measure of the chance that a given event will occur. C, probability. Okay? It has a however many probability of occurring. Okay, look at this little kind of number line over here. You can only have probabilities that lie between 0 and 1, which as percentages would be 0% and 100%, right? You cannot have a 110% chance of something happening, okay? Or a negative 10% chance of something happening. 50% chance means it's just as likely to happen as it is to not happen. So I am just as likely to get heads as I am to get tails on a coin if I flip it, okay? So that's what that kind of looks like. All right, let's go down here, and these are the results of an experimental probability, this down here.
Go back up to the A through.
You betcha I can. I'll just zoom out, okay? So, theoretical probability versus experimental probability. I rolled the dice a number of times, and the results are listed over here in this little chart, okay? So the number, the 1 on the dice, how many times did I roll a 1? Can you tell? 9 times. How many times did I roll a 2? 6 and a 3? 12 and a 4? 6 and a 5? 7 and a 6? 10. So how many times altogether did I roll the dice? If you add those together. 9 and 6 is 15. 12 and 6 is 18. 7 and 10 is 17. Ugh.
25.
So this is 30. This is 35 plus 15. 50?
Did you leave out another 6?
No. I added 9 and 6, 12 and 6, 7 and 10. So this is 9 and 6, this is 12 and 6, this is 7 and 10. I just added each of the 2 numbers together. So 50 times rolling the dice altogether?
Yeah.
Okay. What was the experimental probability of rolling a 6? According to this experiment, yep, 10 out of 50 times I rolled a 6, which would be 1 out of 5. Okay, 1 in 5 chance of rolling a 6. Now, according to theory, in theory, how many times should I roll a 6? 1 out of every 6 times, right? Because there's 6 sides to a dice. So there's a little bit of a difference between experimental and theoretical probability. In theory, 1 out of every 6 times should be a certain number, but according to this, 1 out of every 5 times I rolled a 6. Does that make sense? Okay. All right, so a simple event is an event that has a single outcome. A compound event, which is what we talked about yesterday, I had you write down compound event on the top of your paper, consists of 2 or more simple events, okay? So this is when we are adding probabilities together or multiplying probabilities. So events that cannot occur at the same time are said to be mutually exclusive. So 2 things that cannot occur at the same time. I don't care what the government says, you cannot be, I shouldn't say that while I'm on screen here. You cannot be male and female at the same time. We're just gonna go with that being a rule, all right? Okay, so you can disagree with me all you want, but that's just the way that we're gonna say. Male and female are mutually exclusive. Volleyball and football, you cannot play volleyball and football at the same time. Okay. What else is mutually exclusive? Wrestling and basketball, because they occur at the same time. So wrestling and basketball. How about a freshman and a sophomore? Can you be a freshman and a sophomore at the same time? No.
You can have sophomore
Okay.
classes.
What? You can have sophomore classes, you're right, but like physically actually being in that grade or whatever, freshman, sophomore, you cannot be. So those are all examples of mutually exclusive. Okay? Versus inclusive. I'm going to put inclusive over here. What are some things that are inclusive? Two categories at the same time. What? What's an example of things that are inclusive? Like a person can be in the same category. Yesterday, Jake was in two categories. I don't remember what the two categories were. Boy and
a freshman.
boy and a freshman.
Or,
Oop.
no, a sophomore.
Boy and a sophomore. Okay, boy and sophomore. Can you be a boy and a sophomore at the same time? Yes. But sophomores would include girls as well. And boys would include boys that are not sophomores. So you have to subtract out the boys that are sophomores at the same time. So you would do a Venn diagram that looks like this. So that's an example of an inclusive event. Okay, so let's talk about these two. Tashika's teacher is randomly assigning students a day to present their projects. If 8 students present on Tuesday, I'm going to write this down over here. 8 are Tuesday. 5 are on Wednesday, and 6 are on Thursday. What is the probability that Tashika will present on Tuesday or on Thursday? There's that word.
So you add
Or.
and then
Okay? Or means add. So, I'm going to take the two fractions and I'm going to add them. How many total students are there? 19. He added them together. Okay? So, out of 19, there are, and we want Tuesday, Thursday. So, Tuesday, Thursday, Tuesday, there are 8 people. Thursday, there are 6 people. Can you present on both Tuesday and Thursday at the, like, both of them? Or are you only going to present once? You're only going to present once. So we don't need to subtract out. There would be nothing like in this middle piece over here, you know, nothing in that middle piece. So this would just be, what, 14 out of 19 is your chances of being Tuesday, Thursday? Okay. You guys probably did that a lot faster, but this is the reasoning behind why that works, okay? So, yeah, you eventually will be able to do those a lot faster. B, suppose that of 1,400 students, 550 take Spanish, 700 take biology, 400 take both Spanish and biology. Blah, 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 blah. This is really super confusing. Okay, so I'm going to do a box here, and I'm going to draw a Venn diagram inside of the box. Okay, do this really quick. This will help sort our thoughts out. There are 1,400 total students. So I'm going to put total down here as 1,400. Okay. Spanish, I'm going to put Spanish over here, and I'm going to put biology over here. So 550 take Spanish, 700 take biology, and 400 take both. Okay? All right, good.
How many?
500 take Spanish, 700 take biology, and 400 take both. So how many students take only Spanish and not biology?
550.
Take only Spanish, not biology. There's 550 that are taking Spanish, and 400 of those are also taking biology. So how many only take Spanish?
110 or 150.
150. So 150 equals Spanish only. Does that make sense? How many are only biology?
300.
300 are only biology. Does that make sense? Okay, 400 out of those 700 are biology and Spanish. Okay? All right, what is the probability that a student selected at random takes Spanish or biology? There's that or. But you can take Spanish and biology at the same time, so these are inclusive events. Okay, we have something that we have to subtract out. This problem up here was exclusive. Okay, because we didn't have to subtract anything out. Okay? So we're going to have to subtract a piece out in the middle. All right, so how do we want to add this? How do we add this? What do we do? 550 plus 700 and subtract out the 400 that are counted twice. Out of, what's my bottom number? 1,400 for everything.
Can't you just take 150 plus 300 though? Because we already have that figured out.
But then we're not counting any of the 400,
Mhm.
right? Because the 400 wouldn't be counted at all. So we could take 150 plus 300 plus 400 so that they're counted once. Does that make sense? You could do that. But I mean, it's just the same amount of work as just subtracting the 400. So let's do this. 700 minus 400 would be 300. So 550 plus 300. 850 out of 1400. I can knock a 0 off. 85 over 140. But then I can divide by 5. Oh boy. 85 divided by 5 is 17. 140 divided by 5 is 28. Check that for me. 17 over 28 is the reduced form. If you divide both of them by 5. 85 divided by 5 and 140 divided by 5. Check and make sure that's right.
Wait, do what? Do 140 divided by
80, yeah, 140 divided by 5, is it 28?
1.647.
You didn't divide it right. 140 divided by 5?
20, yeah.
28. 85 divided by 5, is it 17?
85 divided by what?
Divided by 5. I'm reducing
17,
both of them.
yeah.
17. Okay, 17 over 28. There we go. Okay, good. Questions about that? So, when you have people in both categories, you have to subtract them out because they are only one person and can only be counted in one category. All right? Because heaven forbid we have two Jakes, right? Oh, but we do.
Yeah.
But just not at the same one, right? All right, multiplying probabilities. In adding probabilities, the things that we had to worry about were exclusive versus inclusive. So we had to worry about I didn't switch. This guy versus this guy. In multiplying probabilities, we have independent events versus dependent events. Okay? So most of the time, what will happen in independent events, this will occur when you are replacing. So with replace, and dependent events will be without replace. That's most of the time the things that you will have to worry about with multiplying probabilities. With replace, without replace. Okay, good? All right, so probability of independent events. These things have nothing to do with each other. Tossing a coin and rolling a number cube. Okay? If I toss a coin, does it have anything to do with the outcome of the number cube? If I toss a coin and get heads, does it automatically mean that I'm going to get a certain number on a number cube? They have nothing to do with each other. One is not affecting the other one. Okay? So, what is the probability of the coin landing on tails and rolling a 3? So I'm going to do, not heads, tails. Tails, and then rolling a 3. Well, do you see the key word in there? And that's how we know that we need to multiply, right? And, okay, so I'm going to multiply those together. What are the chances of flipping tails? 1 out of 2, 1/2. What are the chances of rolling a 3? 1 out of 6, right? 1 out of 6. I just multiply those together, so the tops get multiplied together. 1 times 1 is 1. 2 times 6 is 12. Beautiful, that's it. Good? 1 in 12 chance of that exact thing occurring. Okay. Example 4, a bag contains 12 red, 9 blue, 11 yellow, 8 green. Okay, here's what I want you to do when they list stuff out like that. Write them off to the side so we don't have to reread the paragraph ever again. 9 blue, I write BLU because sometimes they'll throw black in there, and so I just do BLU. 11 yellow, 8 green, and then it's the second I get done writing those out. What do you want to do?
Read the paragraph.
Not yet. I know at some point they're going to have me take a total. So might as well just add them all up right now. Okay? So I see numbers that are really easy to add. 8 and 12 add up really nicely. What's that come out to be?
Oh, well,
20? 9 and 11 add up really nicely. That is another 20. So 40 total. 40 total. What are we doing? Marbles? 40 total marbles. If 2 marbles are drawn at random, and circle that word or underline that word, not replaced. We are not replacing. What is the probability that a red and then a blue are drawn? So I'm going to write red up top here and then blue off to the side. Okay, the key word was
Not replaced.
and. So and means we multiply. Other keyword was not replaced. You're right. Okay, and means we're multiplying. So red, how many reds are there? 12 out of 40. Okay, how many blues are there? 9 out of 39 because we did not replace, right? Okay, so let's reduce stuff if we can. So 12 and 40. I can divide both of those by 4. If we reduce to start with before we multiply, then it makes life easier. So 12 divided by 4 is 3. 40 divided by 4 is 10. Okay, 9 and 39, will those reduce? You betcha. 9 divided by 3 is 3. 39 divided by 3 is 13. Did you do that in your head? Good for you. Anything else that will reduce? I don't think so. So I multiply straight across. 3 times 3 is 9. 10 times 13 is 130. 130. 9 over 130. That's the chances of that happening. Pretty easy, right? Look for the keywords, okay? For your homework, these two sections will be separated. So you will definitely know for sure that you're going to add and definitely know for sure that you're going to multiply. But when I suck them together in the review and on the test, look for the keywords and or. Or means add, and means multiply. Yeah? Okay, let's go down here. Conditional probability. There's only a couple problems that I assign you for homework. These are just a little bit different, okay? So conditional probability. A condition changes your total number. Changes total number. Okay, I'm going to give you an example before we start with the hard example. 5. Okay, given that I'm talking about a boy. Given boy, what are the chances? Chances, not changes. Chances, I can't write. Chances of me picking a sophomore. What are the chances of me picking a sophomore given that they are a boy? Okay, in this class. The only sophomore we have is Jake, right? Boy, anyway. Okay, so given that we have a boy, your given number goes on the bottom. Okay, now we are not talking about all 2, 4, 6 of you, 7 if we include Claire. Okay, we're not talking about all 7 of you anymore. We are only talking about the boys. So my bottom number goes from 7 down to 4. Okay, my bottom number is that. Now I'm talking about sophomores. Out of those 4, how many sophomores do I have? 1. So I am 1 out of 4. Okay, my bottom number changes from the total to what I'm given, which is only the boys. Okay, does that make sense? So that's how that changes. Your given goes as your bottom number. All right, now I'm. Let me erase that. Okay, let's go up here. A restaurant. At a restaurant, 25% of the customers order chili. If 4% of the customers order chili and baked potato, find the probability that someone who orders chili also orders a baked potato. Was that really confusing?
Yeah.
Especially since I can't read very well. Okay, instead of looking at all of the customers total, we're only looking at the customers who order chili. So this is kind of like my given. I am only concerned with the customers who order chili to begin with. Kind of like I was only concerned with the boys. So my bottom number is 25%. Or you can just leave it as 25 because the percentages are going to cancel with each other. Now we're interested in baked potato. 4. So 4 over 25. And go ahead and convert that to a new percentage for me. What's 4 divided by 25? Like a little less than 25%, 20-some percent.
16.
So, okay, 16%. Okay, so given is my new bottom number. I'm only looking at the chili people rather than looking all at 100% of my customers. Does that make sense? Okay, all right, here. Before we complete this table or answer some questions about it, we're going to talk about totals. So what we did was we did a double-blind study, and we had people that were given the treatment and people that were given the control. So they're given a placebo. Okay, treatment versus control. And 1,600 of the people given the treatment said that their condition was better. Okay, 400 people said their condition didn't improve even though they were given the treatment. So it's kind of like you taking ibuprofen and you're like, that didn't even help because it didn't make me feel better. Okay, so those 400 people were given the treatment, but it didn't help them. All right, The condition improves when they had the control. These 1,200 people are crazy. You know why? They were given a placebo, which is a sugar pill, which is not anything to make them feel better, but they're like, oh my gosh, I feel so much better, right? That's those people. 1,200 people are crazy because they were not given anything, or maybe they just naturally got better on their own, right? But they were given no treatment at all, and they said, oh my gosh, I feel so much better, okay? These 800 people said their condition didn't improve when they were given the sugar pill. That's what should happen, right? Your condition should not improve if you were not given a treatment, okay? So there's that. So out of the total, there were 2,000 people total given the treatment. Do you see that? If I total these two rows up, 200 total people were given the treatment, okay? The control, if I add these two up, that's 2,000 also. So 2,000 given the treatment, 2,000 given the control. How many total people said that their condition was better? How many total people said that their condition, that they felt better? 2,800. 2,800, right? If I add those two things together. Okay, how many people said their condition didn't improve? 1,200. Both of those things say the condition didn't improve. Do you guys see how to read this table?
Yeah.
You have like the intersection, whatever. Okay. All right. So a drug company conducted an experiment to determine the effectiveness of a certain drug. Test subjects were randomly assigned to one of two groups, a treatment or a control. The contingency table. I like that word. That's one of my favorite math words is contingency. This is a contingency table. Or it's called a two-way frequency table, which is this word up here. Those two both mean the same thing. Find the probability that the test subject's condition improved given, circle box, underline that word, given that he or she was in the treatment group. The given number always goes on the bottom. Okay, so given they were in the treatment group. Given they were in the treatment group. You kind of have to read these backwards. So everything after the given is what you're going to look at first. Given they were in the treatment group. How many people were in the treatment group? 2,000 total, right? 2,000 total were in the treatment group. Across treatment. 2,000 total. Now, how many of those people said that their condition improved? Of those 2,000, how many condition improved? 1,600. Okay? Now I can knock off my two zeros. I have 16 over 20. I can divide that by 4. So that would be 4/5. So 4/5 of the people in the treatment group actually had their condition improve. Does that make sense? Okay. All right. The next one. Find the probability that a test subject was in the control group. Given, read everything behind the given that their condition did not improve. So given that their condition did not improve, how many people's condition did not improve? 1,200 total condition did not improve, regardless of the treatment that they were given. Okay, 1,200 goes in the bottom. Now, of those people, how many were in the control group? 800. That's my top number. Does that make sense? So total condition did not improve goes on the bottom, 1,200. Just the people who were in the control group out of those was 800. Okay, I can knock off two zeros. 8 over 12 divided by 4. 2/3. Does that make sense? That was a lot of probability today. Lots and lots. Okay, good? All right, I'm going to stop my recording and see if it worked.